Now we need to bring it to the screen.
Okay, so should I? Oh, yes.
And do you need power? I have a power adapter.
I don't think I need. Yeah, it's full power. That should be fine. Well, just in case. Why not? Okay.
Interesting. So this will be recorded, you see, because this is what you're sharing.
Oh, I see. So let me just with that.
I don't see it.
Okay, is it better now?
Perfect.
Should I turn on my camera or not? I guess I don't need to
Keep
turn
it
on.
on. Maybe you want to write something on the board. And by the way, please stay here so that you
Okay.
they can hear your mic. And of course, you need to unmute.
Yes, I am unmuted. Let me check with online people.
You have power. I don't think it's connected well. I don't see. These are. I think I know what happened.
Yep.
It pushed on this.
Your audio is fine from the online for online people here.
But then you reboot there.
Berkeley time. Perfect.
And the other thing that we tried last time. This is better now. If you do it in green, then not like. Depends if you want to see how.
You know how handsome I am, so.
Okay, so it's exactly 12 minutes past the hour. Welcome everyone. Today is my great pleasure to introduce Hank No. Hank is going to give the guest lecture on workplace optimal join algorithms, which he invented or co-invented. Yeah, please take it away.
Yeah, thank you, Dan. I have quite a bit of materials. I'm going to, skip all of the formality and just go straight to the lecture. For the online people, let me know if you cannot hear me through Slack, a Zoom message or something. Okay, so here's the outline. I will try to define what worst case optimal join is. Apparently, this is actually not very well documented, like what exactly is worst case optimal join. And this will be the second time that some of these acronyms occur in the literature. I'm very proud of them. JAT, VAT, and EAT algorithms. So if you don't remember anything technical about this lecture, those should be the ones you should remember. A worst case optimal join algorithm is the following idea. So in a typical database query processing, you have a query, you have a database in which you have already collected some statistics about the database, unique values, cardinality information, histogram, and so on. And you would like to answer the query as quickly as possible. And for now, let's just consider 4 conjunctive queries. There's no projection for now. Just all queries are 4 conjunctive queries. And a worst case optimal join algorithm is an algorithm that answers this query in the following amount of time. So it will take some time to process the data. So it has to be at least linear in the input, or at least we allow for a linear processing time in the input. And then the time it takes to answer the query is going to be a maximum. So this is a maximum answer size over all databases that have exactly the same profile, because we actually haven't looked exactly into the database. but we allow for, in the very worst case, of all the databases that we haven't looked into, if they have exactly the same profile, let's say the same cardinalities, the same histogram information or whatever, and then take that. So at least the notion is basically saying that there exists at least one database for which our runtime is, you have to spend as much time on that database. So that's what it's optimizing. All right. And now, so this is the theory course. So I'm going to highlight some of the log factors and some query dependent factors. In practice, these cannot be ignored. But in this course, this lecture, we'll ignore those factors. And you may have a question about, whether or not this notion of optimality is even necessary, right? Is there something better than this? Why are we even studying this? Okay. So, for example, you can argue that probably the best thing to do is actually instance optimality. The input size plus the output size. So here we're not maximizing over the worst case instance. Given the database, the best possible thing that you can hope for is just D plus QD, right? You process the input and answer it in linear time. Now, it turns out this is not always possible, and there are proofs of this fact. So we kind of have to, something has got to give, and the current notion of optimality is not for now. Okay? And I have a second guest lecture in a few weeks, in which case I will try to relax this optimality notion even further, because I'm going to give you some examples where this notion is actually not very good at all. Okay. But for now, let's just try to live with worst case optimality.
Is there any intuition for, like, in practice about how much worse is worst case optimality versus instance optimality? Like, are they closely related, or are they like completely different?
They can be extremely different. So the question was, how far is it from the blue quantity to the red quantity? And the red one can be 0. The query can be empty. So technically, they can be infinite. Yeah, so that's kind of a quick answer to that third question. Yeah, so that also explains why this is very hard to do, because instance optimality, it can be 0. All right. So you know very well what a full conjunctive query is. For instance, I will focus on this triangle query as a simplest example, and you must have seen this from the last lecture. We are looking for triangles or the triangles from a given graph. And something more realistic could be like in movie database, you are trying to join a bunch of predicates together. Yeah. All right, now more generally, we are going to model a full conjunctive query with a hypergraph, where there's an atom for every hyperedge in the graph, and then in the atom, the variables occurring in the atom are the variables that are indexed by the hyperedge. For example, in the triangle query, the hypergraph is just the triangle graph. And then there's an atom for every edge in the graph. So there's an edge AB, that means there's an atom whose variables are A and B. For similarly, the edges. So that's called the hypergraph of the query. Okay, so that's the first thing. That's about the query. Now the next thing is what can we put in this profile? Because you can imagine having very sophisticated profiles, and in that case, even computing what is the maximum query size, the green quantity, is actually a completely non-trivial problem. And from Dan's last lecture, you have seen an entropy argument on how to give this this upper bound. So for us, I will focus on one particular type of statistical profile. This is very simple, but in my experience, this is also a very robust profile. It's a very simple and robust. thing, which means it's highly practical. Yeah. So here's how to explain the degree constraints as one of the statistical profile. So imagine you have a base table in which you have 3 columns, actor, movie, and row. And then let's say we collected a frequency vector on the actor column, in which for every actor we counted number of rows that the actor occurs in the table. So in this case, degree of Alice is 1 because only 1 row in which Alice is in. Degree of Carol is 2, and of Bob is 4, and so on. Okay. So this will be like a pretty big vector. And this is not the profile. This is just like an abstraction in order to get what the profile will be. You can also think of this vector as kind of the marginal distribution on the actor column. All right. So now our profile is a summary statistics on this frequency vector. And in this case, it'll be something very simple. It's just the infinity norm of this vector. Okay? So basically, it is exactly equal to 4, because the maximum number of rows that a given actor occurs in is 4. Yeah? So that's our profile. So now we can generalize this idea just a little bit by varying what column you would like to collect this frequency vector. You can do it on the movie column. You can do it on the row column. You can do it on actor and movie together. And so for every one of those combinations, you could have the infinity norm of that vector. So now we are starting to have something like 8 different combinations of these infinity norms, right? You can also generalize it a little bit further and say the following. So a degree constraint is a triple x, y, and n, where x is a set of variables, a set of columns, y is a set of columns, and n is a number, it's an integer. And what we collect is this bound n, in which what we say is that for every possible x, the number of different y's is at most n. Does that make sense? Yeah. So these are just relational operators: select and project. Yeah. So for every possible x, the y degree of x is at most n.
Sorry, so X here is actor, movie, role, or just the subscripts in the D?
Oh, this x here would be actor,
Okay.
and y is movie role.
Okay.
Yeah.
Is the R, are those 2 R's the same R, or like the second R is just some relation, or?
These are the same R. Yeah.
Okay.
This R and that R.
Wait, why do we need to project after we select? Wait,
Oh,
sorry.
good question. So let's say R has more columns than just X and Y. So we, but we are only counting the Y part.
Okay.
Yeah.
Yeah.
Okay. Now in practice, usually we most of the time we just collect for X like one of the columns. But you can imagine cases where you have primary key information. In which, for example, let's say, every actor acts in only one role in a movie. Let's assume that for now. Then X will be actor and movie together. And for every pair, there's only one Y, which is the role of the column, right? So that will capture functional dependencies. So the thing that I want to really point out is that this notion is very robust in the sense that you can capture, let's say, functional dependency by just putting in the right number, right? You can capture, let's say, the unique column count, which is a very common statistics in databases. If you would like to know, if the total number of actors is 100,000, for example, then you will say that X is empty, and then Y is actor, and n is Hamilton. Does that make sense? Yeah, so that will capture the number of unique column counts.
Can we move your computer closer to the screen, so the microphone is closer to you when?
Okay, I will try to stand here with yeah, moving a pointer. Thank you. Although I'm not sure if, okay. I hope the people online can see the pointers. Yeah. Okay, are we okay so far? Yep. So that's degree constraint, right? And of course, the cardinality constraint is just the case when X is empty and Y is everything in R. Then in that case, is the cardinal, you know, the number of rows in a table R. Okay. All right. So here's a like quick summary of worst case optimal join algorithms. So remember that the desired runtime is input size plus the worst case output size. Yeah? And there are basically three classes of join algorithms. And you will see that they are all worst case optimal. Depends on what you assume about the input. Depends on what you assume about the query. And the main insight that I would like to explain is that the algorithm is in the pudding. The proof is in the pudding, and then you look into the proof and you discover the algorithm. Now, you can also mix and match, and here we have actually three co-authors of a paper, Remy and Max and Dan, who mixed and matched these algorithms to come up with, you know, you free yourself from this paradigm, and you can come up with new algorithms that way too. Yeah. Okay, now the runtime of an algorithm depends a lot on how you compute this quantity, this green quantity right here. Okay? Now, it turns out, as probably Dan has somewhat explained from the last lecture, that computing this bound is not trivial. It's not a trivial thing, right? So we have a few kind of approximation, like layers of approximation to this bound. So there's the entropic bound, there's a polymetroid bound, which I'll try to explain. I don't think you had the time to go through it from the last lecture. And then you relax it a little further, it's the chain bound and the AGM bound, which Dan already explained. And then you can even get the integral edge cover bound. Okay? Now, the three classes of algorithms that we will discuss can actually match each one of these bounds. Okay? So the JAT, join at a time algorithm, can match the integral edge cover bound. And then VAT can match the AGM bound, and then inequality at a time will match the polymetroid bound. Now, if the bound is equal to the green quantity, then that algorithm would be optimal, would be worst case optimal. Okay. So the question is really for which class of queries and for which class of statistics do we have the bound being equal to the green quantity? And so in some sense, all of them are worst case optimal depending on the query and depending on the statistics. However, there's an obvious sense in which you know, this IAT is better, is the best, because it's obviously the lowest in the hierarchy. Yep. Okay, so that's a very quick summary of the entire story. Any questions so far? Where is the free join? The free join does not give an improvement in terms of the asymptotics. But if you know, there's a distance from the theory to an actual implementation, and I think free join actually exploits the statistics in the data better. So you know, these asymptotics really do not tell the whole story, and I think there's a lot of that. So it's in a row with NPR. I think so. Yeah, I would. Yeah. Okay, so now I will have to talk about the green quantity, which is kind of a similar lecture from what Dan. Go ahead.
Oh, just real quick, are all of those bounds like subsets of each other, or do they overlap in some parts? Or which of the studies?
So these bounds, so these inequalities are for all instances. So which means that this really is a hierarchy. Now there are queries for which the gap between consecutive bounds are, there's actually an actual gap, like asymptotic gap. So does that make sense? Like they like kind of like they are like containing one another in some ways. Yeah. Yeah. Okay. So we will probably need to spend some time talking about polymatroids. So we'll be considering set functions, which are functions from subsets of variables of this query to real numbers. Okay? So you can think of the quantity that we assign to a subset of variables to be the marginal entropy on that subset of variables. You don't. So last time Dan defined entropy already, but very roughly speaking, you should think of entropy on a set of variables X as the degree of uncertainty, like how much uncertainty you have on this set of variables X. And then there's this really important quantity, is the conditional entropy. So so h of y given x, now I will define it to be just h of x union y minus h of x. But you should think of it as how much uncertainty do I have on y given that I know x? So fix x to be something, then how much uncertainty do we have on y? And then a polymatroid is one of those set functions in which the following holds. So the degree of uncertainty on the empty set is 0. There's no uncertainty when there's nothing. And then the more variables you have, then the more uncertain you'll be, right? So h of x is less than h of y if x is a subset of y. So more variables mean more uncertainty. And then submodularity, which says that if you know more, then you'll be less certain. Yeah. So so h of y given x and z is certainly less than h of y given x alone, because here you know more, you know a little bit more, you know with z, right? So the degree of uncertainty you have about y is going to reduce if you know a little bit more. Yeah. So that's all submodularity is. It's a very easy way to remember these inequalities if you think about uncertainty. It's very intuitive. And go ahead.
I just wanted to make sure, let me actually unmute myself. This is important. Oops, it doesn't work. Do people remember the Shannon inequalities from last time? These are Shannon inequalities. And what we kept it kind of unsaid last time was that every entropic vector satisfies the Shannon inequalities. But what about the converse? What do you think? Is it the case that any such vector that satisfies the Shannon inequalities is an entropic vector? Very hard to answer. It was a major breakthrough in the late 90s when Yang and Zhong discovered that no, it's not the case. There are such vectors that satisfy all the Shannon inequalities. You only need 4 variables, and which are not entropic vectors. So the vectors that satisfy the Shannon inequalities, they deserve a name. And that name is, they're called a polymatroid. Yeah, so a polymatroid is a vector that satisfies all Shannon inequalities. An entropic vector is a polymatroid, but the converse is not always true.
Yep. Go ahead, Remy.
So maybe to that, so the definition of entropy function is actually not this set of inequalities.
No.
So how do we define entropy function?
Yes, so an entropic function, I didn't give the definition here, but it's a function is entropic if and only if there exists a distribution whose entropy is that function. Yeah, it is sort of like a tautology, and yeah. Okay, so I just want to emphasize on what Dan just said, right? So if you let gamma n denote the polymetroid, the set of all polymetroids over n variables, and gamma star n denote the set of all entropic functions also over n variables, then gamma star n is a subset of gamma n, namely that every entropic function is a polymetroid. However, the converse is not true. For n more than 3, 4 or more.
Okay.
Yeah. So this is a strict containment for n starting from 4 or more. So every entropic function is a polymetroid, though. So there's a reason why we want to mention this. That's because we can use entropic functions to give a bound, the green quantity that we are interested in, given that the input satisfies the degree constraints.
So to clarify what Dan said, Dan is saying that there are functions that satisfy these inequalities, but there do not exist a distribution such that they're true. Yeah.
Precisely, yeah.
I'm actually thinking whether we should discuss this on Tuesday in a week and a half. We have the next lecture, because I think it's such a cool topic that I think it deserves a deeper understanding. We'll come back to this.
Okay, so here's the main theorem came out of the paper that Mahmoud and Dan and I had in 2017, like really my favorite paper that I've been a part of. And it goes like this. So the green quantity that we want to bound, I can't really see, how do I turn this into, there has to be a way to turn the, never mind. Annotate?
To the left. The fourth from the right.
I can't see. It's too dark. Oh, there we go. Yeah, thank you. Spotlight, where is it?
Yeah.
Okay, awesome. Thank you. Oh, I can make it like that. Okay, there we go. Okay, so this is the green quantity that we want to bound, right? We want to upper bound, but computing it is pretty hard.
Can you remove that window?
Oh, yes.
Sorry, when you say the green, the green quantity, I don't see any green quantity here.
Yeah, I'm sorry. Yeah, so I didn't color this. It was green on the previous slide, but it's not green here. But I'm trying to kind of. Do you see the mouse hovering over it?
Yeah, I see the
Yeah.
the mouse.
Just the worst case output size bound of a full conjunctive query. And I abbreviate that with green quantity. So just think of it green as worst case output size bound for now. It is upper bounded by a maximum or a sup over the entropy over all variables of the query, okay, where H ranges over all of the entropic functions over n variables, and H has to satisfy the degree constraints. And what are the degree constraints? The degree constraints are the constraints of the form H of y given x is at most log n for every degree constraint x, y, and n, as we mentioned earlier. So degree constraints, there's a combinatorial notion which says for every x, the number of y's is at most n. But there's also the corresponding entropic kind of notion, which is the conditional entropy is less than log n. Okay? Now the proof of this is, and I will give it as kind of an exercise. it's basically the same proof that Dan gave last time. There's only a slight generalization to be conditional entropy. That's all there is. Okay, so the proof of this is very simple. So, however, because this gamma star n is a really complex object to handle, so the next best thing is to enlarge the set a little bit into the set gamma n, which is a set of polymatroids. Now, gamma n is great because now it's all linear constraints, right? Submodularity is linear, monotonicity is linear. So all of them are just linear constraints. And DC, the set is also linear, right? You see h of y union x minus h of x is less than log n. So we have just a linear program, and we use it to bound. The problem, though, is that this linear program is pretty big because the number of constraints on gamma n is exponential. So that's the main issue. If you just want to use this to bound, then it will not work for queries of, like 20 variables or so, or more.
So this linear constraint is a reasonable assumption because we're assuming that like no variable goes to more than m elements. Is that how I should read it or something?
By elements, do you mean?
Like, why is it reasonable to assume that DC holds?
I would assume that the database has collected statistics on the base tables, and they are given as inputs to this problem. So you can maintain, for example, a number of unique unique values in a column using some.
I guess I'm asking where does log n come from?
Oh, log n come from the fact that so if you look at any distribution, the maximum entropy occurs at uniformity, in which case, you get log of the support. Yeah.
So this n is the maximum degree of y given x. And this part of the statistic that you store.
Right.
Question.
Yes, go ahead.
Why should I care that I can pass this into a linear program in practice? I mean, I like integer bound and it makes me happy, so I do this.
Right. So the question was, why do we care if this is a linear program? What if it's a convex program or something more complicated? So I think there are two things. So one is kind of computability in a reasonable amount of time. But the more important thing is the worst case optimal join algorithm. Like, how do we come up with an algorithm that will match this bound, right? If the bound is so complicated, it's hard to even analyze any algorithm at all.
So we're going to match the yellow bound.
That's right. We'll try to match the yellow bound with an algorithm. And Grace, I hope you can see the yellow color this time.
The yellow highlight I can see.
All right, awesome. Thank you. All right, so now the quantity that we're interested in, which is the red one, we cannot really compute, but we'll focus on this yellow color, okay, the polymeter one. Okay, so let's look at some examples. This may be fun. So the triangle query is something that you have seen last time. And let's say we have three statistics for this triangle query. So the size of R, number of rows in R, number of rows in S, and number of rows in T. Now, in this case, the corresponding degree constraints are, given nothing, the number of different ABs is R, right? Given nothing, number of different BC is S, and similarly for T. So those are corresponding degree constraints. And then if you write this down in terms of the polymatroid bound, then it will be h of AB, given nothing, is h of AB, is less than log R, h of BC log S, and h of AC less than log T. So any guess as to what the bound is if we solve the yellow linear program? The AGM bound. Yep, it turns out it's exactly the AGM bound. Okay, so the polymatroid bound is actually equal to the AGM bound, even though it's not obvious. It's not completely obvious from the description. Now, you might have noticed that the AGM bound was actually a bound that was polynomial in n. Like you can write down a linear program that fractional edge cover. Yet in our case, it's not completely obvious how you go from an exponential number of constraints to something that's polynomial in n, but that's a different story. But for now, let's just say that we can prove this quantity. Okay? In particular, if R, S, and T were exactly equal, then you will get the n to the 1.5. This is the famous AGM bound or Loomis-Whitney inequality. This was known for a very long time. In fact, I'll tell you a fun story. The first time I learned about this inequality was, there was this IMO problem from 1970 something, maybe either before or after you have taken the IMO exam. There was a problem to prove this inequality in the IMO exam.
Yeah, it wasn't on my idea.
Okay. Yeah, so in any case, I wanted to say that this was known for a long time. Yeah. Okay, so let's do something a little less trivial or less less trivial. So here I have also the triangle query, but now I also know one extra thing, that B is a primary key of the relation S. So AB, BC, and AC, but B is now known to be a primary key of relation S. Okay? So that means that we have the degree constraints as we had from the previous slide, but also the extra one that says for every B, the number of C's is 1, is at most 1. So now can you take a guess as to, well, let me write down the linear programs, right? The DC is just like before, with one extra thing, which is the conditional entropy of C given B is 0. Right? Log of 1 is 0. So guess what the bound is now? Yes, go ahead.
Was it like the minimum of R and T?
Minimum of R and T. So
Minimum of 3 and T.
yeah, that's very close. Yeah. So obviously, if you know R, then you can use the B to C FD to get to C, right? So certainly R is a bound. Yeah. But you can also take like just S times T, essentially. Right? If R was humongous, then R is not a good bound. If R was like a billion, and then S and T are very tiny, then you maybe just take the cross product of S and T. And that's exactly what the bound gives. So we have to kind of reason combinatorially in our head about it. But then if you put it into a linear program, it's going to give exactly what a human reasoner would have done. And this is certainly more significant in terms of asymptotics, because now it's down to linear instead of n to the 1.5 like before. Okay, so another example, if you have like just a cross product of two relations, but then you know that A plus B is 5, then in this case you will know there's an FD going back and forth, A to B and B to A. And I will save you the trouble. The bound is going to be the minimum of the two quantities. Yeah? But we didn't really have to do this like on a case-by-case basis. Just give it to the linear program, is going to solve it for us. Okay, there's one more non-trivial example, but I will leave it as an exercise for you to do at home. And the bound turns out to be like a square root of RS and T. Okay, so all of this is just to say that the bound, the polymatric bound, is a very intuitive bound, as you put it in. Yeah. Okay, so now that we know what the bound is, which means we know the target runtime that we would like to achieve is, so let's look at some algorithms to achieve this runtime. So there are 3 classes of algorithms. I have only one slide on one join at a time algorithms. So, and it's this slide. So, from your database systems course, you probably have known that the typical query join plan for triangle query looks something like this, right? You can join RNS first, RNT first, or SNT, or RNS. You can construct an instance for which the intermediate result is quadratic, which is greater than the green quantity, sorry, Grace, which is greater than n to the 1.5. Yeah, so that means that a JAT query plan is suboptimal for this query. And it doesn't matter which query plan. Like for all query plans, there's this input instance is going to be pretty bad for all possible query plans. And however, if you just, if the query is just like joining two tables, then this can be optimal. This algorithm can be optimal. So it depends on the query. Okay, so here's the first thing that may be non-trivial. So let's look at the second class of queries.
Sorry for going back. So earlier you said that the polymetric bound can be computed by the near program, but near program is really huge, so it's not really tractable. So is there a tractable algorithm for computing the polymetric bound?
Good question. So the question was if there's a tractable algorithm for the polymetric bound. So first of all, the complexity of the bound is open, is unknown. Yeah, we don't even know if it's NP-hard or not, which is a very annoying problem. And then there are actually some classes of inputs for which you can compute it in p-time. But we don't have kind of a lower bound for it. Yeah.
And then for the entropy bound, we don't even know if it's computable.
That's right. Entropic bound is open whether or not the bound is even computable to begin with. Okay, so let's look at VAT algorithm. So there's a little bit of detour because I'm going to use Holder inequality, and I don't know if I can assume that you know this inequality. And it goes like this. So so imagine you have a matrix Aij, so m rows and n columns. Okay? So and every entry in the matrix is non-negative. And suppose that there are coefficients lambda 1 to lambda n. So there's one coefficient for every column of this matrix, okay? Such that the one norm of this is at least 1, which means that the sum of the lambdas is at least 1, and it's non-negative. Yeah? So this is R plus. So there are coefficients, one for every column, and it's non-negative, all of them. Then the following holds. So imagine you take, let's think about the case when n is equal to 2. That means that there are only 2 columns. Yeah? 2 columns and then m rows. Yeah? And then so we have 2 coefficients, lambda 1 and lambda 2. Lambda for column 1 and lambda for column 2. So you should think of this quantity as kind of the dot product of those 2 columns. But raising to, column 1 is raised to lambda 1, and column 2 is raised to lambda 2. Okay, does that make sense? So the sum is just a dot product of those 2 columns. So then the inequality says that, if you were to take the dot product of these 2 columns, then you can upper bound that by kind of taking a summary of column 1 first, like you sum over column 1 and then raise to the power, and then sum over column 2 and raise to the power. So it's an inequality that allows you to push the sum inside of the product, and you will see this theme occurring very often. Okay, now this inequality is just a generalization of that. So instead of taking dot product of 2 columns, you have n columns. Each one of them has a coefficient. And then instead of taking this n-way dot product, you can just take a norm of each of the columns and then multiply the result together. So that's the inequality. Yeah. Yeah, so in the 2-column case, that's Cauchy-Schwarz. it says that the dot product of two vectors is less than the product of the lengths of two vectors. You can prove it using Jensen's inequality, and I think in some books they even actually give the credit to Jensen. All right, so why do we need it? So let's go back to the triangle query with the AGM bound for the moment. In the triangle query, last time Dan had shown you that the number of triangles in the given query is bounded by the following quantity. It's bounded by r to the lambda r times s to the lambda s times t to the lambda t. Now, probably you have done this with lambdas all equal to 1/2, but yeah, it's basically the same bound. Yeah. So the number of triangles is bounded by this product, where the lambdas will have to satisfy the following inequalities. But pairwise, they have to be at least 1. Okay. So that's another way to state the AGM bound for the triangle queries. And there's a reason why I wanted to state this in this more general form. So you can plug in like 1/2, 1/2, 1/2 everywhere, or you can put in, if any two of them is equal to 1, then this will hold, right? Because you get 1 + 1, 1 + 0, 0 + 1. So those are basically the 3 solutions of this problem. Okay, so let's assume that we have the lambdas for now. Let's try to come up with an algorithm whose runtime is exactly given by this bound. And if the bound was tight, then the algorithm will be worst case optimal. As I said earlier, the main insight that we gained over the past 10 years or so is that the algorithm is in the pudding, is in the proof, right? So let's actually prove this bound. And then you will see that the algorithm actually jumps out like immediately, almost. Okay. So let's give a proof of this bound. So here I'm going to kind of do a little bit of reasoning with the query itself. Yeah. So this is a triangle query, right? So suppose that I fix a slice of this query, just one particular value A for now, right? It's like a selection on the query. Yeah. And I'm going to try to bound the size of this for a given A first. Yeah. And then when you sum over all A's, and you get the bound for the entire query. Now, in order for BC to be in the output of this subquery, then BC has to be in S for sure, right? But BC will also have to be in the cross product of the selection of R on A and the selection of T on A. Yeah, so BC is in the intersection of those two things. Now, what that means is that the intersection of two sets is bounded by the minimum of the two sets. Right? It certainly cannot be more than the minimum of the two sets. Yeah. So then the quantity we want, which is, all of the triangles with the fixed A, is bounded by the minimum of these two sets. Yeah? Now the minimum of two quantities is bounded by the geometric mean of the two quantities. So if you were thinking of lambda s as equal to 1/2, then that means that minimum of x and y is bounded by the square root of x and y, of x times y. Does that make sense? Yeah. Minimum is square root of the product. It's bounded by the square root of the product.
Are you saying this holds for any lambda s, or just for in particular for lambda s equals 1/2?
This holds for any lambda s, positive lambda s. And so all I'm doing is just to put in, that's exactly the geometric mean of the two. And it holds for any positive lambda s. Okay, and finally now I can use the fact that lambda s, lambda t form a fractional H cover. So then 1 minus lambda s is less than lambda t. right? If you go back to the previous, see lambda s, if you move lambda s to this side, and 1 minus lambda s is less than lambda r, and 1 minus lambda s is less than lambda t. So we just use this fact to distribute this lambda into the right places. So 1 minus lambda s is less than lambda r, and 1 minus lambda s is less than lambda t. And finally, we just apply Holder. So the triangle, the number of triangles is the sum over all a's of the selection, right? The selection we just proved to be bounded by this quantity. So this is just the sum over all a's of this quantity. And this is exactly the sum of the dot product. Remember, we just discussed on the Holder inequality. So then you can push the sum inside, right? So we kind of take the norm of the vector, push the sum inside, and take the exponent afterwards. That's Holder inequality. And this, the sum overall, selection is just the size of R. So we proved this inequality just by that extra step. So there were two things that we used. One was Holder, and the other one was the fact that the lambdas form a fractional edge cover. Okay, so now let's try to extract an algorithm from this proof. Okay, so the algorithm was basically, let's actually do a for loop over a's and try to compute this quantity, like this selection of the output on the a. Right? So that's what the algorithm is. Just for every a in common between R and T, and then in the inside you will kind of iteratively do for every b in common between R and S, subject to the same selection. And then for every C in the intersection, report ABC. So if you think of it, this is not nested loop join. This is backtracking search, right? You start from the first value of A when there's a match, and you condition on it. And then look for the next B that will match. So this is why this is called one variable at a time algorithm. Find the first A, and then find the B that will match subject to the A that we have, that is fixed now. And then condition on A and B, find the C.
Smells a little like Yanakakis. Am I missing something? Is it because we do in the innermost loop, we're taking two variables, that it's more than just Yanakakis?
I think this is let me put it this way. So there's some commonality with Yanakakis if the query structure is a little bit simple, but in general, Yanakakis is more about dynamic programming, and this is backtracking search. So it's like the other side of the coin from Yanakakis. Yeah. So dynamic programming, you have to save something that you have computed before, but here we're not saving anything. Yeah, here if you hit a if you hit anything, you just backtrack, right? So it's orthogonal to Yanakakis, I would say. Right.
This is all sense. Does anything interesting change if it's on X or
so the question is, what if the semantic was back semantic, right? So I would say that if you kind of simulate a back semantic with an extra count column, then everything will go through. But I haven't thought about the case when actually R, have duplicates in it, because here I'm assuming everything is sorted, so there's really no advantage in doing back semantic. I haven't thought too much about it.
And looking up these keys in the for loop is fast because we already have statistics.
So here I'm assuming that we have already built an index for our S and T in the variable ordering that we used to do this backtracking search. So that is basically in the linear pre-processing step of the algorithm. But you are right, if we have to do that, then you kind of have to build an index. So that's one of the drawbacks of this class of algorithms. Okay, so how does the proof work? Well, the proof is exactly that. Basically, computing this section of the query, for a given A, is basically to compute this intersection, right? And if you look at the algorithm, you can see that we can compute the intersection in time that is the minimum of the sizes of the two sets. You can prove that inductively. And because you can compute the intersection in the minimum sizes of the two sets time, you can now just apply the proof that we just did for the upper bound. So the minimum of the sizes is upper bounded by this quantity. And just like copy it over. And summing over the time, you will get exactly the AGM bound. In fact, how we came up with this algorithm was basically just to stare at the proof of the upper bound for long enough. All right, now this may not be very convincing. I'll give you the next thing that is I would say much more convincing. And the idea is of proving anything is you prove it for n equals 3 and let 3 go to infinity. And then hopefully you get it. Now that's not true for 3 sat. It turns out that from 2 sat to 3 sat there's a gap. But in most cases, I think 3 is a good number to think about. Yeah. All right. So in general, what happens in general for full conjunctive queries and not a triangle anymore? So in this case, we have a fractional edge cover for the query hypergraph, right? That's the same AGM bound. And the proof goes exactly the same. You just kind of repeat exactly what we just did, right? So let's fix a section of the query for a particular A value to be little a. Yeah. So in this case, in the body of the query, of course, you only look at the atoms that has A as a variable. Right, so you fix it to be A. And then you repeat exactly the same proof like before, and push the sum over the product to get the summation inside, and you get the AGM bound. Yeah, that's precisely the same proof. There's a little bit of manipulation, but not much. There's no new insight that you gain from doing this exercise, except for maybe the math looks more impressive because of the generality of the bound. Okay. And then, so here's the algorithm. The algorithm goes like this. Let's loop over all values A's in the intersection of the atom that has A in it, right? So and then what we do is we recursively use exactly the same algorithm to compute the little a section of the query on that value. Right, so it's a very highly inductive one variable at a time algorithm. And then we just report the output. We just attach A to every tuple that is emitted by the recursive algorithm. So I find this to be even more convincing than the triangle example. Right? It's very inductive in nature. And the runtime is precisely exactly that. It's the AGM bound plus the input size. It follows the same script as the triangle case.
So this runtime holds for any fractional edge cover bound.
That's right.
Because you only needed it to show that the minimum is less than the weighted geometric mean, and that holds for any weighted weights as long as they sum up to greater than 1.
Right.
In practice, how do you choose the order in which you use variables?
Yes, excellent question. So the question was, in practice, how do you choose the variable ordering? It is exactly query planning, the physical query plan. And variable orderings have a humongous effect on the runtime. So one kind of heuristic would be, you want to choose variable orderings for which the more selective ones come first. And yeah, that's a different lecture altogether.
Wait, okay, but it does say that any variable ordering gives you this bound. Is that true?
That's true. Yep, that is true. Okay, however, so let's go back to the degree constraint for the moment. So the AGM bound by itself only applies to cardinality constraints. Like, remember our degree constraints are of the form, for every fixed x, the number of y's is at most n. So the AGM bound only applies to cases where x is empty, because we only get the cardinality constraints and not the actual degree constraints. So in general, we have a bound that is a little bit general than the AGM bound, which is called the chain bound. And you can repeat the same argument and then it will run in that time. However, the chain bound is parameterized by a variable ordering, and this bound could be more or less depending on this variable ordering. And that's kind of the query planning issue, exactly as you pointed out. Yeah. Okay, so the last topic on Shannon flow inequalities, the EAT algorithm. So I have about
20 minutes.
Oh, excellent. Yeah, I'm just right on time. Go ahead, Yushi.
Is sideways information passing related to this at all?
Yeah, so sideways, so SIPs are yeah, it's very similar, I would say. Yeah.
That's the Anakakis thing again.
That's the intersection of flying data.
Yeah. So maybe let me put it this way. So SIPs and Yanakakis and this class of algorithms they share something in common, which is subquery decorrelation. So this is something I should have mentioned. So the reason why the binary join plan is really not good for the triangle query is because when you are joining two relations, there's a third relation that's actually correlate with the subquery that you are doing, right? So by pushing things inside the subquery, you are able to kind of, reduce the search space. And it's the same idea with Yanakake, same ideas with SIPs, which is subquery decorrelation. You want to make use of information that is outside of the subquery processing.
This all connects also to the top-down versus bottom-up evaluation stuff.
Right.
And I wonder, you made a space argument before that Yanakakis is going to have a space array, but you're building indices as well. So,
That's true, yeah.
I don't know if you sorted through all this, but it smells like there's equivalencies in there sometime.
Yeah, so this is why, free join, maybe ask Remy to give a guest lecture on free join. The system side of things is still open, really. Oh, sorry.
But you said at the beginning that this was for join plus without projection.
That's right.
Why?
Okay, so I'll give you a short answer for why we had to assume that the query is a full conjunctive query. So let's say the query has no free variable. Let's say it's just a yes/no question. Then the output size bound is 1, right? It's either yes or no. And it's really not a good framework to analyze such queries. Because even in the worst case, the output size is just 1. So yeah, we have another lecture on the topic of, what if there was some projection and how do we kind of bound the output size in that case? Okay, so the next thing is Shannon flow inequalities. So I will be mindful of time, and I would like to provide more examples than and the theory. So let me see how much I can get through. So recall that we have this bound hierarchy, and I kind of explained a little bit an algorithm to achieve either the chain bound or the AGM bound, right? Roughly speaking, you do it one variable at a time, and you get there. So let's see if we can get to this polymatroid bound, and how do we get them? Which is this quantity. Now, I do want to point out that there are some queries or some input statistics for which the AGM bound or the chain bound is equal to the polymatroid bound. So in those cases, this algorithm is already sufficient. There's no need to go beyond that, right? But here, let's consider cases where that's not the case, where there's actually a gap from the polymatroid bound to the next bound. So I'm going to skip this part actually. So there's some linear programming duality and all of that. And here is something I want to mention. So a Shannon flow inequality is an inequality of this form. So we are given a bunch of degree constraints, right? And let's just say that for every degree constraint, we have a coefficient delta. I haven't told you how to get to the delta yet, but let's say there's a non-negative coefficient delta, one for every degree constraint. And assume that somehow this inequality holds for every polymatroid, H. Then if that's the case, if the deltas was so big, maybe, that this inequality somehow holds, then the inequality is called a Shannon flow inequality. Okay? So I'm going to skip the kind of linear programming duality explanation of this. I just want to mention that this, from Dan's lecture from last time, is a generalized version of Shearer's lemma. If you don't remember, no worries. I'll give you some examples to kind of illustrate the main concept.
Sorry, I'm just a notation here. What's V?
What is the
V on the left of the yeah.
Oh, yes. V is a set of all variables in the query. So the size of V is n.
Okay, and X and Y are just standard degree constraint. This is just X, Y, N is just a standard degree.
That's right. So X and Y are subsets of V, and then N is a number. So X is a set of variables which are all in V. Y is a set of variables also in V.
Y contains X.
And in this notation, Y contains X. Yes. Thanks, Dan. I should have also written maybe H of Y union X. But it's in this particular notation, Y I will assume that Y is a superset of X. Okay, so let's look at some examples and it'll become clear. Okay? So again, for the triangle query, so this inequality, I think Dan actually played around with this inequality from the last lecture. This is a Shearer inequality, and it's also a Shannon flow inequality. And you can prove it that it holds for all polymatroids in the following way. And this may be different from the Bolo-Bastom proof that you provided last time. Okay? So maybe it's worth it to go through this proof because, again, algorithm is in the pudding, which is from the proof. So I will give the proof first, and then you will see how to get an algorithm out of that. Okay, now this proof is basically from a paper by Radhakrishnan in 2003. It was a very, very interesting. I'm sorry, I probably misspelled his name. Maybe not. Anyways, so the proof goes like this. So I'm going to start from the right-hand side. And let's focus on one of these quantities for the moment. So HAB. Yeah? I will start from the right-hand side and then somehow show that it's greater than twice the left-hand side. Yeah? So the sum is more than 2 times H of ABC. So the first thing is kind of just a rewriting. So H of AB is H of A plus H of B given A. Remember that h of b given a is h of ab minus h of a, so there's nothing, we haven't really done anything, we're just doing some rewriting. Yeah? So this blue quantity is decomposed into a sum of two blue quantities. All right, so now we are going to apply submodularity. So in this case, I'm applying it in the following way. So h of a is greater than h of a condition on BC. Remember that the degree of uncertainty will be less when you know more, right? But now, if you are conditioning on BC, then you know more, right? So the thing will be less. Yeah. Now the other three terms are just being rearranged. So h of BA is put over here, h of BC is put over here, h of AC is over there. Okay? So this was just one submodularity step.
So the red stuff, the H and BC is not coming from so much. That was just.
Yeah, that's just some rearrangement, and I put them in red because in the next step they will be combined together. Yeah, this is to prepare for the next step. Yeah. So now we are just, so now you see that this becomes HABC, right? Because H of A given BC plus H of BC is H of ABC. So this is called composition. Yeah. So now we compose it into H of ABC. And the next thing is applying submodularity again. So now we have H of B given AC, because now we are conditioning on more. So it goes down again. And now compose them, and we get H of ABC. So that's a proof of this Shannon flow inequality. Obviously, it holds for every H for which submodularity holds. Okay, so that's a proof. Now, how do we get from this to an algorithm to answer the triangle query in n to the 1.5 time? So I have another example. I'm not going to skip this part. So here's the algorithm. The algorithm goes like this. So we somehow magically get a hold of a Shannon flow inequality, just like the one we just discussed. And then we magically come up with a proof sequence. We just saw an example. And then from this proof sequence, there are basically the following steps in the proof sequence. You can do composition. Remember, we saw this composition just now. We can do decomposition, right? So you can condition on X. This step we didn't have in the example, but in a general case, you might need the step where you move from H of Y down to H of X. If Y is a superset of X, you might need this step. And finally, this is nothing but submodularity, right? So composition, decomposition, submodularity, and you have seen all three of these in the example just now. Okay. Okay. So a proof sequence is just a conversion from the right-hand side to the left-hand side using a series of these guys. Okay. And now we want to convert a proof sequence into an algorithm. How do we do that? It goes like this. So the composition will become a join. A decomposition is actually partitioning the data. Partition the data into parts. This is kind of, you can guess where it's going. It's in some ways it's pretty obvious in hindsight. So if you have to move from many variables down to fewer variables, and that's the projection. And finally, submodularity is actually a no-op. It doesn't do anything. It's just an intermediate step to get to the next step of the algorithm. Okay. All right, so let's not do the formality, just work through the triangle example again. So here it goes. Triangle example. So first, I'm going to define something this is the partitioning step, but I have to define what my partitions are in advance. So I will define the heavy part of R to be all of the tuples A, B in R, for which the degree of A is more than square root of n. And the light part to be the degree of A to be less than square root of n. I'll tell you, there's a math to decide on this threshold if you have to, if you have a question. But for now, let's just say that someone gave you the threshold already. Okay? So this partitioning, and the main idea is that, you know, in order to avoid a big intermediate, you really want to avoid joining two heavy things together, like two heavy hitters. You really want to avoid that. And the proof actually gives you a recipe for when to avoid those things. Okay, so now let's look at the proof, right? So we have a proof sequence. We are going to run in parallel kind of a join algorithm. So for every copy of this H thing, I'm going to have the same copy, but now of the relation, of the input relation. So there's a blue relation. Right? So the first thing we do is decomposition, right? This is decomposed. This means that this will be decomposed into heavy and light. I'll show you the actual query plan for now. I'm just driving the parallel between the proof and the copies of the relations that go through. Okay, so decomposition becomes kind of partitioning into heavy light. And then this submodularity step is a no-op. It's just a rearrangement of the terms. And then a composition step is a join. Okay, so this will join this red part and this red part into a new intermediate relation. This is the heavy intermediate. And then another join, which means you have to join two of the green relations. And that's how you get to the result. And so this is not a query plan. I'm just drawing the parallel yet. So let's look at the query plan. So query plan goes like this. So when you do partitioning, what does that mean? It means that you are doing a query rewriting, basically. You write the blue relation as a union of the heavy and the light part of this relation, right? Now, you can do pull out the union. So now you have two subplans. One plan contains heavy side and one plan contains the light side. And now, following the script from the proof, we are joining the heavy part with S. So that's an intermediate relation. Also, in the proof, you see there's a green part that joins the light part with T. That's the light relation. And finally, once you have a relation on ABC, you can just use it to filter, you know, join with T. This can be done in time that is linear in the heavy, right? Because you have a relation that contains everything. So you can just do a lookup or something, hash join, whatever, to filter the results down to get the final results. So in some sense, this T part is just to filter. It doesn't really add to the asymptotics of the algorithm. Yeah. Now, it's very easy to show. Maybe I'll leave this as one of the homework problems. The heavy part is less than n⁻⁵, and the light part is less than n⁻⁵.
SNT or symmetric here, like I could have joined R heavy with T, right? Or is there some reason I can't?
No, you cannot. If you join R heavy with T, then you might get something more than n⁻⁵.
It's heavy with respect to the degree of A.
Okay.
Right. Exactly. Yeah. Yes.
I understand what mechanically you did between the previous slide and this slide, but I think a bit going backward, are all these relational expressions, they have entropies that are from the previous slide?
Yeah, so so the question was whether or not there's actually a tight one-to-one correspondence between the two slides. It's actually, in general, is an open question still, in the following sense that this example. I mean, we cannot make this example to work in general. Okay? In the actual algorithm, you will see that there's a step in which you have to partition this heavy light into more parts than just two. Unfortunately, it'll be like a logarithmic number of parts. It's more complicated than this. So that means that we have to suffer kind of a terrible factor, a polylog factor, so log to a huge power. So it only works in theory. It doesn't work in practice for an arbitrary query. However, there are some classes of queries for which this works perfectly well, like this triangle query.
Can I ask sort of like how many of these heavy light sections there can be total? Because at least my very sort of my intuition coming from sort of like trying to apply some other techniques to this is that the number of regions where like the number of possible regions where you have like heavy and light is the solution to some multi-parametric linear program, which is sort of a piecewise linear decomposition.
Right.
And we know from Kannon's partition theorem that in the worst case, you can have exponentially many such regions. So I'm curious, like if that actually ever shows up in here.
Certainly, yeah. So unfortunately, it could be even doubly exponential in the query
Oh, yes,
size.
exponential, yes.
So yes, so the answer to your question is that this query plan can get extremely unwieldy very quickly. It works like, neatly on a very small example, but in general, further research has to be done to narrow down the class of queries for which it can be made practical.
Just to oh, sorry, go ahead.
Oh, quick one, do you ever have to partition intermediate results? So here we are, okay.
Yes, you do. Yeah.
So just to clarify, the algorithm that we saw earlier, that simple nested for loops, that is optimal for the AGM bound. It's super simple and Hank has implemented it many times. And it works extremely well. If you want to match the better upper bound that also takes into account the degree constraints, then the only way we know how to do it is with this difficult reasoning about light and heavy and with all the additional complications. If you don't do it, then you run the generic join, the algorithm that we showed earlier, and which is super efficient in practice where it's efficient, and it matches only the AGM bound that is aware only of the kernel. That is the distinction.
It can also match a Chen bound, so it's a little bit more than just the AGM bound, but certainly there's a gap with the polymatrix bound. Yep. Okay, I think I'm perfectly on time, which just give you a hint of the the three classes of join algorithms, EAT, VAT, and GAT. And there's a lot of open questions because so far we have only focused on degree constraints. You can imagine other constraints. And then, the question of computing the bound, the question of designing algorithms that will match the bound, even for degree constraints, as you can see, there are open problems there. So I'm very excited because, database research has been around for 60 years, and there are still a lot of open questions, which is great. Thanks for listening.
Thanks, Hank. Was there a question over there? Good. So just a reminder, next week we don't have any lectures, neither on Tuesday nor on Thursday, because we have a workshop going on at Simon's, and actually Hank is going to lead the workshop, and it is on fine-grained complexity and query evaluation. It's going to be quite interesting. So I strongly recommend that you look up the program and come to some session that.
Could you also please post the slides online that they're on the course website yet?
Yes.
Thank you.